This is what we call the pigeonhole principle, which again, it's a very logical idea. If you have n plus 1 or more objects, and you're going to place them into, well, we're calling them holes because of pigeonholes, but into n categories, then at least one of those must have 2 or more objects. It's a fairly logical thing. If I've got more objects than there are holes, then one of those holes has got to have more than one object. Basically what it's saying. Now, let k be the maximum number of objects you can put in n holes without having more than one object in a hole. I'm going to prove that k is less than n plus 1. Here's my proof. I'm going to do it by contradiction. I'm going to assume k is actually bigger than or equal to n plus 1. Now, the maximum number of objects equals n. Remember? We said maximum number of objects you can put in n holes without having more than one in a hole. So the maximum number of objects I could have would be n. And that's if there was one object in every hole. But that would mean k, therefore, has to be less than or equal to n. There's my contradiction straight away. I've assumed k is bigger than or equal to n plus 1, but then logically, k has to be less than or equal to n. Well, it can't be both. Thus, it cannot be true that k is greater than or equal to n plus 1. Therefore, k is less than n plus 1. So that's sort of a proof of the pigeonhole principle. Let's actually see it in action. That's probably more what we need to know. Oh, by the way, to generalise, you can think of it this way. If k or more objects are placed into n holes or categories, then at least one hole must contain k over n. Now, I don't know if you're familiar with this notation or not. That's what's called the ceiling function. Has anyone ever heard of the ceiling function? Okay. The ceiling function, so it's like you've drawn brackets but left the bottom bit off. So like, basically it means round up regardless. So if you've got an answer of 4.1, the ceiling function of 4.1 would be 5. The ceiling function of 4.3 would be 5. 4.7 would be 5. 4.0000001 would be 5. So basically, ceiling function, round up regardless. There's your formal definition. If the ceiling function of x is equal to y, then x must be somewhere between y minus 1 and y. Always round up. Okay, so integers are going to be selected from this group of integers there. What's the least number of integers needed to ensure that there are a pair of numbers that add up to 15? How do we look at this? Well, if we look at our list of numbers, there are 5 possible pairs that will add up to 15 out of those numbers. 3 and 12, 4 and 11, 5 and 10, 6 and 9, 7 and 8. Okay, they are going to be my pigeonholes, if you like. So I'm going to pull out a number and I have to place it in one of those sets. And in fact, I'm being told which ones to place where. 3 will go there, 12 will also go there, and so on. So that's how many holes. Now, the pigeonhole principle tells us that 6 integers will need to be selected. If I've got 5 holes, then if I've got 6, one more than the number of holes, then I must be guaranteed 2 in one of those holes. So this is telling us that 6 integers, if I select 6 integers from this list, I must get a pair that adds up to 15. 6 are the objects that we're going to be placing. Way of doing it using the ceiling function. So we're saying that k divided by 5, right? The number of objects, that's what we're trying to work out, divided by the number of holes. We're saying the ceiling function of that is 2. We want at least 2. Using this inequality then, we're saying k over 5 is in between 1 and 2, not including 1. Right? So the inclusion is on the 2, but not on the 1. Multiply by 5, I get that k has to be in between 5 and 10, but not including 5. So the smallest number that I need is 6. I mean, 7 would do it as well, 8 would do it as well, 9 would do it as well, 10 would do it as well. But it's asking us for the least number. 6 would be the smallest. I've got 50 points that we're going to plot in a 7 by 7 square. What's the maximum distance apart? That 2 closest points. So we're going to plot these 50 points. We're going to find the 2 that are closest together. What's the biggest it could be? What's the biggest distance that could be? Well, what I know This is why the numbers are what they are here. The square could be divided up into 49 1-by-1 squares. Now I have to place my dot somewhere in this square. If we now think of those 49 new squares that I've drawn, there's the pigeonholes. And the dots are going to go in one of them. I've got 49, but I've got 50 points to place. So that's telling me there must be one of those squares at least that has 2 dots in it. So there's 49 holes. We know there must be a square that contains at least 2 points. So if there is a square that contains at least 2 points, well, the closest distance, now think of one square, you're going to place 2 points in a square, you want the distance between them to be a maximum. Where would you place those 2 dots? In the corners. It's like saying I'm going to draw a right angle triangle, I'll put a dot at either end, that's got to be the longest. Well, what would the length of that diagonal be? Be the square root of 2. So that would be the maximum distance. Yes, they could be closer. Like we could have maybe 3 dots in one of them. That would be less than. We're asking for what the maximum distance apart 2 dots could be. We have a group of n people. Or we're going to prove that in our group of n people, there will always be at least 2 people with the same number of friends. It is not possible for one person to have no friends and, like it is possible for someone to have no friends, but it is not possible for one person to have no friends, but also have a situation where another person has n-1 friends. Okay, who wants to volunteer to be the person that has no friends? Okay, you have no friends. Okay, so one person has no friends. That leaves us with 23 people, yeah? Another person will have 23 friends. Okay, you can't be friends with yourself. You now have 23 people to choose from as a friend, but you can't have him because he's got no friends. So it's impossible for that situation to happen. I'm going to pick one of those situations. Only one of those situations can happen. So I'm going to assume it's the situation where, because let's think we're friendly, eh? Nobody has no friends. That's the one I'm going to pick. Nobody has no friends. All right. Therefore, the possible number of friends a person could have would be 1 up to n-1. So there's n-1 different number of friends a person could have. So n-1 holes, categories, call them what you like. But hang on, we said we've got n people. So there's your pigeonhole principle. If I've got n people, then when I'm placing them into which category, oh, you've got 1 friend, okay, you're going in that category. Oh, you've got 3, okay, you're going in that category. Once I've done n-1, I've still got a person left over. They've got to go in one of the categories. So there must be someone with the same number of friends as someone else by our pigeonhole principle. We're going to write 16 numbers. I could invite 16 people up to write positive integers on the board. No, I don't care what you pick. You can pick any number you like. Right? So 16 people, at least how many numbers will have the same remainder when divided by 5? There will be 5 possible remainders. 0 goes in it exactly. Remainder 1, remainder 2, remainder 3, remainder 4. Remember, you're going to write 16 integers on the board. We're going to place those 16 in one of those holes because it's the number you write is either going to have a remainder of 0, 1, 2, 3 or 4. So the question is, how many do we end up with? It will be the ceiling function. 16 numbers you're going to pick. I'm saying there's 5 categories for it to go into. So it'll be the ceiling function of 3.2. So at least 4 numbers will leave the same remainder. Ready for this one? This is a good one. A computer is going to generate random 3-letter words. But 3-letter words in our definition, remember, can be nonsense words as well. How many words need to be generated to ensure that there is a word in our list that has been generated 8 times? Well, the number of possible words would be 26 cubed. Because 3 letters, 26 by 26 by 26. So that is going to be n. They're our pigeonholes. So we have 17,576. Going to generate a word, we can put it in one of those pigeonholes. So we're looking for the K. When divided by 17,576, that ceiling function will give us an answer of 8. Goes back to our definition then. K over 17,576 must be between 7 and 8, might be equal to 8, but it must be between 7 and 8. Multiply by, and there's our range for K. How many words need to be generated? Well, once we go past 123,032, we're in the range that we want. So therefore, 120,033 words need to be generated to guarantee it's been generated 8 times. Time for fun.